This video on this topic, which is voting, I showed you the outline of a simple strategic model of voting, and then we worked through a numerical example where I showed you the preliminaries of how to calculate equilibria in models like this. So today what we're going to do is we are going to look at some general properties of these voting models. We are going to see under equilibrium behavior whether Condorcet's results come through. So let's take the general voting model that we set out. There are two states of the world. The defendant is either guilty or innocent, and one of two decisions have to be taken whether the defendant is going to be convicted or acquitted. And voters get their private signals based on which they cast their vote. So one question is, how does the voting rule matter, or what's an optimal voting rule in a situation like this? And then we'll explore other issues. So let's first ask the question, is there a voting rule under which voters will vote sincerely, the way they would have voted if they were a judge? Let's suppose parameters are such that sincere voting means voting according to signal. So guilty signal leads to a conviction vote, or innocent signal leads to an acquittal vote. Okay, so this slide tells you about what the voting rule has to be to get this kind of informative voting. So let's do a thought experiment. Suppose that all the signals of all the different voters will get pooled together. They will be pooled together, and it will become public information to all the voters. So suppose all the voters know all the signals. So then when will they want to vote for conviction? Well, the answer to that is that there is a threshold value, right? There's some K star. If at least K star of the N signals are guilty signals, then their common preference would be to vote for conviction. If it falls short of K star, then they would want to acquit the defendant. So how do we know what K star is? Well, if you look at this calculation, this is the probability, the posterior probability of guilt, given that the number of guilty signals is K, some K. So you can calculate that using Bayes' rule, and here's the value. Now, obviously, this posterior probability will be increasing in K, right? The more the guilty signals in the pool of signals, the higher is the estimated probability of guilt. Now, remember, they want to convict if the posterior probability of guilt is above Q, right? So that gives us this threshold property that there will be some K star such that when the number of guilty signal hits K star, at that point, the conditional probability of guilt crosses over and goes above Q, and conviction becomes the optimal decision. So let's call this K star the statistical rule, right? So if everything was public information, then this would be the minimum requirement for conviction to be optimal. Now here's a theorem which comes from the Austin Smith and Banks paper, which is really the first paper which laid down this sort of model and studied it. So the result is pretty simple. It says that sincere voting is informative and rational if and only if the minimum number of votes needed for conviction is exactly K star. So the optimal voting rule, in other words, is K star. The statistical voting rule. All right. So if the voting rule is set at K star, then everybody would want to strictly vote according to their signals. So why is that? The reason is not very hard to see. Suppose we have set the voting rule to K star. Then if a voter is pivotal, that means that the rest of the voters have exactly K star minus 1 guilty signals, right? So there has been K star minus 1 conviction votes. That's why he's pivotal. That's why his vote is going to make a difference. So if K star minus 1 other people have voted for conviction and everybody's voting sincerely, then K star minus 1 is the number of guilty signals out there. Now, if our voter gets a guilty signal, then that means that the total number of guilty signals has become K star. K star minus 1 from the others and 1 from him. So in that case, he would like to convict. However, if our voter gets an innocent signal and he's also pivotal, that means that the total number of guilty signals out there is exactly K star minus 1. So the posterior probability then falls below Q, the threshold of doubt, and in that case he wants to acquit. Okay, so this tells us that if we knew all the parameters and if we were designing the voting rule, then we would like to set the voting rule at exactly K star, the statistical threshold, and in that case the voters will play pure strategies. That will be a Nash equilibrium. Everybody will vote strictly according to their signals. Now, that is difficult to do. For example, when voting rules are decided for, let's say, parliamentary decisions or courtroom decisions, various different problems come up. They all have different parameters. In some problems, the P is high. In other problems, the P is low. In some problems, the threshold of doubt that people have in their mind, that has a high value. In other, it has a low value. So as the parameters of a problem changes, the optimal voting rule changes. But usually we don't have the luxury of designing a new electoral system every time a problem comes up, right? So for all parliamentary votes, we either have a majority rule in place or we have a 2/3 majority rule in place, but it has to be a one-size-fits-all voting rule. Okay, so the voting rule will not always be possible to be set at this ideal K star. So if the voting rule is something else, it's not the optimal voting rule, then what happens? What kind of equilibrium can we get? And that's what we have to study. And so the next thing I'm going to talk about as I work through the kind of equilibria we get in these models, I'm mostly going to be talking about the paper by Feddersen and Pesendorfer from 1997. So before I get into the maths of it, let me tell you the sort of conceptual highlights of this paper. What are the points this paper is making? One of the sort of significant points the paper makes is the following. If somehow we had sincere voting, voters voted as if they were making the decision in isolation, like a judge. If that were the case, then raising the minimum number of votes needed for conviction lowers the probability of convicting an innocent person, right? You raise the bar, you require more votes needed to get a conviction decision, then you will naturally lower the probability of wrongful convictions. That's a given, and that's easy to see. However, as we saw, except in very special cases, we were just talking about it in the last slide, except in very special cases, voters will not vote sincerely. They will vote strategically, and they may sometimes randomize after seeing a certain signal. So we have to take that into account, and we have to study equilibrium voting behavior and what happens under that. So under strategic voting, this is the most interesting result in the Feddersen Pesendorfer paper. Under strategic voting, as you raise the bar for conviction, both error probabilities may go up. So you may increase the probability of letting go guilty people, but at the same time, you may increase the probability of convicting innocent people. Both kinds of mistakes may become more likely if you raise the bar, make it harder to get a conviction. Now, what is the broad intuition behind this somewhat counterintuitive result? Well, let's think about it. It arises from the logic of pivotality. Rational voters calculate their posterior probabilities based on two things, if you recall. One is what signal they have observed, but also on the event that they are pivotal, that in the rest of the voters there's a tie and his vote is going to change the decision and make it conviction or acquittal. So here's the broad intuition. If it's simple majority rule, then a voter being pivotal means the rest of the voters are kind of split 50-50. Yeah. So their signals about guilt or innocence is also kind of split down the middle, right? Half of them have got guilty signals, half have got innocent signals. So those signals cancel each other out. So in that case, a single voter has a very strong incentive to look at his own signals and vote according to his private information. But now consider the case where the voting rule has been made more stringent and has been made unanimous rule, unanimity required for conviction. So in that case, what does being pivotal mean? Being pivotal means that everybody else has voted for conviction. Okay? So if you think that they are voting strictly according to their signals, that means in a jury of 12, let's say, 11 votes have been cast for conviction, so there are 11 guilty signals out there. So even if our voter has observed an innocent signal, because of 11 other guilty signals, he has a strong incentive to ignore his private signal, ignore his information, and vote for conviction anyway. Now, that cannot be equilibrium behavior, of course, because then the votes of others also has no information content. Everybody is voting for conviction no matter what. But you can see the direction in which things are going. When it's unanimity rule, being pivotal is a kind of information which tilts the balance heavily in favor of the defendant being guilty, or there being a lot of guilty signals out there. And that is what makes a voter inclined towards voting for conviction, even when his own signal is pointing in the other direction. And this is fundamentally what is driving it. So there are two effects. One effect is the pure brute force effect of more votes being needed to get a conviction. But the voters under this voting rule also become more prone to voting for conviction, right? So there's a plus and there's a minus. And what Feddersen Pesendorfer show in their paper is that that the greater willingness of voters to vote for conviction is an effect that may dominate, and that is what may lead to the perverse result. They further go on to show that under unanimity rule, Condorcet's results fail, including the asymptotic result. So even if the jury becomes infinitely large, the probability of making mistakes may remain bounded away from zero. It will remain bounded away from zero. So there will be always a strictly positive probability of making mistakes. The flip side of that is, for voting rules which are not unanimity rules, which are interior voting rules, right? So examples, simple majority rule, or even 2/3 majority rule, or 90% majority rule. Any voting rule which requires a strictly interior fraction of votes in favor of conviction for a conviction decision. Any such voting rule has the property that as the jury size grows large, Condorcet's result is true, meaning the error probabilities go to 0. Let's look at the calculations to find the equilibrium. Remember that Feddersen and Pesendorfer, when they solve this model, they only look at symmetric responsive equilibria, right? So these are equilibria where all voters at the end of the day are playing identical strategies, and these strategies are best responses to each other. So in this kind of model, there can be basically one of 3 types of symmetric equilibria. This is the first case on this slide. Let me maximize this. Okay, so for the rest of the analysis, we'll take the prior to be half. That's without loss of generality, really. And we'll take that conditional probability matrix for the signals to be symmetric. So PG and PI are both equal to some common value P. So here's some notation. Sigma of G is the probability that a voter votes for conviction when she sees a guilty signal, and sigma I is the probability she votes for conviction when she sees an innocent signal. And as we defined earlier, that if we want to look at responsive equilibria, we want these sigmas to be different from each other. Now, here's some further notation, gamma sub G and gamma sub I. These are, so what is gamma sub G? Gamma sub G is the probability that when the true state is guilty, a particular voter, one individual voter, will vote for conviction. And gamma I is when the true state is innocent, the probability an individual voter will vote for conviction. All these probabilities are probabilities of voting for conviction. Keep that in mind. Now, these expressions are fairly intuitive. So, for example, the first line, when the true state is guilty, with probability P, the voter will get the correct signal, in which case, according to our notation, she has the probability sigma G of voting for conviction. And with probability 1 minus P, she will see the wrong signal, in which case the vote for conviction has probability sigma I. Now, when the true state is innocent, then these two probabilities flip around, right? So she sees a guilty signal only if the signal is wrong, and that has 1 minus P probability. And she sees an innocent signal only if the signal is correct. So that's the probability here. Now, one feature is not very hard to see. After observing a guilty signal, the posterior probability should be strictly greater than after observing an innocent signal, right? In both cases, she will take into account the fact that she's pivotal. That's part of the equilibrium logic. But in one case, she has got a guilty signal. In another, she's got an innocent signal herself. So obviously, the guilty signal will bump up the probability estimate a little more. Okay, so here are a couple of features. Suppose after observing a guilty signal, a voter randomizes. So suppose sigma G is strictly interior. It's between 0 and 1. Now that means after observing a guilty signal, her posterior probability estimate will be exactly equal to the threshold of doubt Q, right? So that means after an innocent signal, instead of a guilty signal, if she observed an innocent signal instead, then her probability estimate would be below Q, so she will strictly prefer acquittal. In that case, sigma I is going to be 0, right? So she doesn't vote with conviction with any positive probability. The other case, suppose she randomizes when she sees an innocent signal. So that means after innocent signal, her posterior estimate is again exactly equal to Q. She's indifferent. The belief is exactly at the threshold of doubt. That's why she's randomizing. So in that case, instead of an innocent signal, if she saw a guilty signal, then she would want to vote for conviction for sure, because her belief will in that case be strictly above Q, right? So basically we can have one of three kinds of equilibrium. One is pure informative voting, that after guilty signal, vote for conviction for sure. After innocent signal, votes for acquittal for sure. That's one kind. The other kinds where there's actually some mixing going on, the mixtures will either be some sigma after guilt and 0 after innocent signal, or some sigma after innocent signal and 1 after guilt, right? So in other words, the voter cannot randomize after each of the two signals. She will only randomize after observing one signal, and if she observes the other signal, she will play a pure strategy. Okay, so three types of equilibria. Type 1 is basically informative voting. There's no real randomization here. Sure vote for conviction if the signal is guilty, sure vote for acquittal if the signal is innocent. Now, what are the conditions needed for this to be a valid equilibrium? Well, here are two posterior probabilities. The expressions are long, but they're not hard to calculate. The first expression on the left-hand side here is probability of guilt, given that the voter is pivotal and given the voter's signal is innocent. So this calculation should work out to be less than Q, the threshold of doubt. Only then she will want to vote for acquittal for sure. And this is the other posterior calculation. This is the posterior probability of guilt given pivotality and given a signal of G, a guilty signal. This posterior has to be above Q. So the two posteriors after the two signals have to be on two sides of the threshold of doubt. Only then can this kind of equilibrium exist. Then you have equilibrium of type 2, where randomization really happens after observing an innocent signal. So if that has to be the case, then after observing an innocent signal, the voter has to be indifferent between convicting and acquitting, which means the posterior probability that you calculate has to be exactly equal to Q. That is what induces indifference. So there's a lot of algebra crunching that you can do, but it's not very hard, so I'm not going to go through all the details. But basically this indifference condition pins down the value of sigma for you. We saw that in that simple example with two voters. So this is the second type of equilibrium. Then there's the third type of equilibrium, where randomization really happens after observing a guilty signal. And there the indifference condition will have to apply to that case. In other words, the probability of guilt, conditional on being pivotal, and a guilty signal should match the threshold of doubt, and that indifference condition, that equation, helps you pin down the value of sigma, which is on this slide. Okay, so for any set of parameters, you cannot have more than one of these equilibria, right? It either has to be type 1 or type 2 or type 3, depending on what the parameter combination exactly is. Okay, so let's come to the main results of the paper. First result, suppose the voting rule is interior. right? So alpha is the fraction of votes that are required to get a conviction. And suppose alpha lies strictly between 0 and 1. It can be very high, it can be very low, but it is not hitting the boundaries. That's the requirement. So what is this result saying? It is saying that for strictly interior voting rules, there always exists a large enough n, or a threshold of n jury size, so that for all juries bigger than that, you have a symmetric responsive equilibrium of one of the three types that we described in the previous slides. But more pertinently, the limit probabilities are 0. So the probability of wrongful convicting an innocent person, the first kind of mistake, as well as the probability of acquitting the guilty, the second kind of mistake. As n goes to infinity, as the jury size gets very, very large, these error probabilities, they converge to 0, right? So very large juries almost surely do not make an error of either type. They're kind of godlike, they're almost perfect, they almost always make the right decision. And what is interesting is that the requirement is very mild, that the voting rule has to be just interior, right? It doesn't have to be the optimal voting rule which matches the statistical rule that we saw earlier. It doesn't have to be that. It can be any interior rule, but still asymptotically the error probabilities will go to 0. So let's try to understand the reasoning behind this result, get a sketch of the outline of the proof. Now, one way you can do is purely mathematically. So the model can be solved. You can have closed form solutions. So I showed you on previous slides how to calculate the equilibrium randomization, the probabilities. And you can just through brute force calculation check this result. So these are the expressions that were derived for sigma I and sigma g, and you can take the limit as n goes to infinity. Now let's not do a sort of a mechanical proof like that. Let's try to get an intuitive understanding of why this result is true. So I'll give you an outline of that. There are basically two steps to try and prove it. The first step is this line over here, that as the jury size gets very large, this inequality can be proved. Alpha, remember, is the fraction of votes needed for conviction. It's a voting rule. And remember what gamma G, gamma I are. It's gamma G is the probability that when the true underlying state is guilty, any single voter will vote for conviction. And similarly, gamma I is the probability of voting for conviction when the true state is innocent. So this is saying that these two conditional probabilities of voting for conviction in the two different states, they have to lie on either side of alpha. Okay? Now, once we establish this, the next part is pretty simple. Then the rest of the proof goes pretty much like the proof of the statistical Condorcet Jury theorem. Basically, let's move ahead, assuming the first line to be true. Let's understand the second line, and then I'll come back to the first line and or the first step, and I'll give you the rough reasoning why that is true. Now, assume the first step is true. Then, as n becomes very large, when the true state is guilty, the expected fraction of conviction votes has a mean gamma g and some variance around it, right? Now, as n becomes very large, this becomes almost a degenerate distribution by the law of large numbers, right? Most of the probability mass is concentrated around gamma g, and there are very thin tails on either side. So with very large probability, almost surely, in the true guilty state, when the true state is guilty, the fraction of votes for conviction will be more than alpha because the mean is higher than alpha. Similarly, when the true state is innocent, every individual voter has this gamma I probability of voting for conviction. So the fraction of conviction votes in the jury has a mean of gamma I and some variance around it. But as n goes towards infinity, that variance approaches 0. So the fraction of conviction votes will almost surely fall short of alpha, the conviction threshold, right? Okay, so the second step is simple. Let's go back to the first step. Why do we claim that this gamma G and gamma I have to lie on both sides of alpha? So to give you some understanding of that, I drew this picture. So let's look at this picture. So suppose not. Suppose gamma G and gamma I are both higher than alpha. And the logic would be similar if they were both lower than alpha. Remember one thing, gamma G will always be higher than gamma I. Okay? Because under gamma G, more people will get or maybe expected to get guilty signals. So the overall expected number of conviction votes will be higher. Okay, so now look at this picture. The green and the red curves are the densities of, so on the x-axis we have the fraction of votes cast in favor of conviction. In the guilty state, it's the green curve which captures the density function. In the innocent state, it's the red curve which captures the density function, and these are the respective means. So in both cases, so now let's think about a voter being pivotal. If a voter has to be pivotal, then among the rest of the voters, the fraction of the fraction of votes cast in favor of conviction has to be below alpha. It has to be just below alpha, right? So in other words, it has to be drawn from the tails of these respective distributions. So if you have a guilty state, the probability that the other voters will cast conviction votes short of alpha will be drawn from this red tail. And if the defendant is truly innocent, then the probability of being pivotal will fall in this green tail, right? Now, when the number of these curves are actually binomial distributions, right? And as n goes towards infinity, these distributions approach normal distributions. Now, the basic intuition is that if n is very large and gamma G, gamma I are both higher than alpha, both these tails, the red tail and the green tail, are very thin. In other words, the probability of being pivotal in either of these cases is going to be very small. But the fundamental point is this: because the green distribution has a higher mean, the ratio of the tails of the red distribution and the green distribution approaches 1 as n grows towards infinity, right? Both of these are unlikely events when the jury size is very large. The true number of, or the true proportion of conviction votes will be drawn from either of these tails. Each of those probabilities goes towards 0. But the green tail goes towards 0 infinitely faster than the red tail, because the green tail is coming from a distribution with a higher mean, which is further away from alpha, right? Now, when you apply Bayes' rule, you're trying to understand that if you're pivotal, if the proportion of conviction votes has fallen in one of these two tails, which tail is more likely? And as I just said, as n is going towards infinity, the probability that it's being drawn from the red tail is infinitely higher. So that ratio approaches 1. So by Bayes' rule and updating, when a voter is pivotal, the voter will think that that the true state of the world is innocent, because gamma I is closer to alpha and the red tail is bigger, much bigger. So the probability that the defendant is innocent will loom very large. The voter will think that with very, very high probability approaching 1, the voter is innocent. So even if he gets a guilty signal, he will vote to acquit in this case. So remember that we are looking at these mixed strategy equilibria, right? So when he gets an innocent signal, he's supposed to randomize. So his belief on guilt should be exactly equal to Q. But if the picture looked like this, his belief on guilt will actually approach. Okay, so under any interior voting rule, Condorcet's conclusions turn out to be true in the class of equilibria that Feddersen and Pesendorfer are looking at. Namely, the error probabilities go to 0 as the jury size increases and becomes very large. Now, one implication of that is that we don't have to worry too much about the voting rule as long as we have access to a large decision-making body. Instead of fine-tuning the voting rule, if you have a lot of participation, a lot of crowdsourcing of the decision, you can make very large juries. The probability of making a mistake can be pushed arbitrarily low. So that's good news. But now let's turn our attention to unanimity rule, and that's one of the main messages of this paper, that unanimity rule or corner rules have bad properties, and those are the only rules where Condorcet runs into trouble. So here's one result. So we are going to look at two conditional probabilities. So assume unanimity rule. You can calculate what is the probability that the defendant is innocent given that the decision is to convict. This is one conditional probability. The other conditional probability will be the reverse of this, probability of conviction given that a defendant is truly innocent. Now these are of course different from each other. But the two theorems, this one and the next one, they basically say that both these conditional probabilities remain bounded away from 0 even as the jury size goes towards infinity if the voting rule is unanimity. Okay, so this gives you exact expressions. Again, these can be derived using the equilibrium that was derived. And this is the other theorem, the second theorem, which says that as n becomes very large, this probability, this is the randomization probability, remember? So if you have unanimity rule, when they get a guilty signal, they vote to convict. When they get an innocent signal, they randomize. So this is the probability of voting for conviction when the signal of the voter is innocent. This approaches 1 as the jury size goes to infinity, right? So this is that force that I was talking about earlier. With very large juries and unanimity rule, each voter almost always votes to convict. They are very, very prone towards conviction. Even if they get an innocent signal, they convict with very large probability, and it approaches 1. And the two conditional probabilities, probability of convicting an innocent person and acquitting a guilty person, both of these remain bounded away from 0. So let me try to give you a sort of a sketch of the reasoning why these results are true, and I'll focus on the first result. This is the first conditional probability, right? If this remains bounded away from 0, you can prove that the other one will also remain bounded away from 0. So probability that given that we as a jury have convicted a defendant, what is the remaining probability that this person may be innocent, right? What happens to that probability? Well, it is bounded away from 0 for the following reason. Here on this line, we are measuring posterior probability of guilt. Okay, so probability of innocent will be 1 minus that. So, this point here is the probability of guilt given that a voter is pivotal before looking at the signal. Now, of course, once we are at this point, then the signal comes through, and it may either be innocent or guilty. So a voter sitting here, based on just pivotality, the voter has updated her beliefs. If she gets an innocent signal, of course, the belief on guilt will drop down somewhat. And if she gets a guilty signal, it will jump up to another point, right? Now, these revisions are being made on the basis of one single signal. So these jumps will be finite, and they will be independent of n, the jury size. So keep that in mind. Now, the equilibrium that we are looking at involves randomization. So when a voter gets an innocent signal, the voter randomizes between the two votes. So therefore, the belief after getting an innocent signal should be exactly equal to the threshold of doubt, Q, right? So when it jumps down from probability of guilt given pivotal, it jumps down to Q. So when it jumps up to some point. Now, the distance between Q and this higher point has to be finite. It is based on just flipping one single signal, right? And this is independent of n. So in any equilibrium, the probability of guilt after taking into account the voter is pivotal and her signal is guilty is some finite distance above Q, and it's independent of the size of the jury. So that's why it's bounded away from 1. You can keep on adding n, you can keep on increasing the jury size. This point, this higher belief, won't budge from here. And notice that this probability we are talking about is exactly probability of guilt given conviction, right? So look at the conditioning event. If a voter is pivotal, that means everybody else has voted for conviction. And if the voter's signal is guilty, then this voter also votes for conviction. So everyone votes for conviction, and by unanimity rule, conviction happens, right? So this conditioning event, being pivotal and receiving a guilty signal, is equivalent to the defendant being convicted. So this is exactly that probability. So that probability remains bounded away from 1. So the other probability that the defendant is innocent, given that we have convicted him, that remains bounded away from 0. So that explains why unanimity rule doesn't, in the limit, doesn't eliminate the probability of the jury making a mistake. Here are some figures. So in the paper, they simulate a version of the model. They take particular parameter values, and so they take the accuracy of the signal to be 70%, and the threshold of doubt to be half, 0.5. And this graph shows you the probability an innocent defendant is convicted as a function of the jury size. So there are two interesting things to observe here. First, even as you increase the jury size, the asymptotic line here is above 0.2. It's somewhere between 0.2 and 0.25, right? So there's even with very large juries in this example, there's more than a 20% chance that an innocent person will be convicted. The other interesting thing to note in this figure is as you're increasing the jury size, this error probability convicting an innocent person, this is actually increasing. So Condorcet's conclusions break down on both fronts. Asymptotically, we don't have perfection from the jury, and larger juries are creating higher probabilities of making a mistake. This is the other graph, which plots the probability of making the other kind of mistake, which is, this is the probability that a guilty defendant is acquitted. So 1 minus this, what we are plotting here, is the probability of making the other kind of mistake. So notice here also the same features apply. It remains bounded, so asymptotic efficiency doesn't happen. More importantly, as you're increasing the jury size, the probability of convicting a guilty person is coming down. So the probability of letting go a guilty person is going up. So the other probability is also going up. So these two features, these two graphs tell you that under unanimity rule here, as the jury size increases, there's a greater chance of making both kinds of errors. Once again, Condorcet's conclusions do not hold. Here's a numerical example which gives you the exact values, and again you can see that, for example, so this is with 12 jury members, which is the size of actual juries in the US and other countries, and here this row gives you various voting rules. So 7 is simple majority rule, 7 votes required for conviction. And we are increasing the threshold of conviction all the way up to 12. When it reaches 12, that means unanimity rule. And if you look at the probability of mistakenly convicting an innocent person, that's this row here. So under simple majority rule, it's less than 1%. It's 0.4%. But it steadily keeps increasing, and when you get to a jury size of when you get to the unanimity rule, it has increased to 0.7%. And similarly over here, and this one gives you sigma, the randomization probability. Okay, so just summing up, Condorcet raised this question of, he laid out for us some instrumental value of democracy, that if you have more participatory decision making in a context where every person has bits and pieces of information, he tried to push these conclusions that larger decision making bodies will make better decisions, and if we can create a lot of crowdsourcing in the decision making, create very large decision making bodies, then we will, for all practical purposes, be able to eliminate the probability of mistaken decisions. And the strength of that conclusion, the engine is really the law of large numbers. When there's a very big jury, there are lots of different independent sources of information. So if those pieces of information could be pooled, if all the information could be made public, that would be very powerful, right? That is standard. But what happens in a voting context is that voters are trying to achieve two things. One, they're trying to make information aggregation. Through their votes, they're trying to convey their bits and pieces of information that they have. But at the same time, in the same exercise, they're also trying to reach a decision, right? So they have one instrument, casting their vote, and that instrument is trying to fulfill two roles. One is to create an information bank, and the second is to make a decision. So for this reason, the problem is non-trivial. So what this recent literature, starting from Austin Smith and Banks, has done is that it has game theoretically modeled the voting game and how rational voters will behave. And we apply the sort of standard equilibrium concept like Bayesian-Nash equilibrium. So applying this kind of game theoretic modeling of voting, we ask the question that, does good decision making happen, and in particular, was Condorcet right? And the answer is a qualified yes, that the Condorcet was right. Larger juries do better, and infinitely large juries are almost godlike, provided the voting rule is not extreme, provided the voting rule doesn't set a threshold which is very, very high, in particular, provided the voting rule is not unanimity rule. Except for that case, Condorcet's conclusions are right. But under unanimity rule, a lot of inefficiencies happen. So the message is that requiring unanimity for a certain decision is bad, generally bad, especially when we have access to a very large electron.